We're going to do all of 4-3 today, so hang on to your seats. Okay, we're going to start with Riemann sums. Okay? Don't write this down right now. We're just going to talk about this. Okay? Right now we've been using technically trapezoids and rectangles to approximate the area under the curve. Okay? And we said, how do we get more accurate area?
More subdivisions.
More subdivisions, okay? The more subdivisions we have, the more rectangles we have, the closer our approximation is going to be to the actual area. All right? So, what we're actually going to do is we are going to, okay, we are going to add up an infinite amount of infinitely small rectangles. Okay? So, we're going to take these rectangles and we're going to make them as small as we can. And we're going to add them up, and that is going to give us our exact area. Alright? So, in order to do this, we're going to have to go back to Unit 1 and use the concept of a limit. Okay? We want an infinite number of rectangles under our curve. So what we're going to do is we're going to take the limit of the sum of these rectangles, okay, where this limit is going to fit infinity, meaning we're going to add up an infinite number of rectangles that are infinitely small. And that will give us our exact area. Okay. Today is the day where we start to see the bridge between all of this summation stuff that we've been doing and our integrals that we worked on a couple weeks ago. Okay. What this is actually representing is a definite integral. Okay? A definite integral from A to B is actually finding the area under the curve, like we've been doing with our rectangles. So when we find the area of these rectangles under the curve, we're actually finding a definite integral from A to B. So now we're putting numbers on our integral. Okay, so go ahead and write that down. Tomorrow is when we'll get into actually using our antiderivatives to evaluate this. But for today, we're going to focus on the area concept. Okay? The integral from A to B of f of x dx means we're finding the area under the curve from A to B. Okay? We're going to accomplish that by adding up an infinite number of rectangles in that integral. Okay? Now, I want to go ahead and talk about some properties with these definite integrals and what they mean as far as our area. Okay, and then we'll get into how to do this right here. Okay, so first property is this. If we take the integral from A to A, that is representing the area from A to A. If we're not going anywhere, if our end point is the same as our beginning point, there is no area that we are finding. Conceptually, does that make sense? Yes. Thank you, honey. If our interval has width 0, there's no area to find. Okay. All right, the integral from A to B is the same as the opposite. Okay, the integral from B to A is the same as the opposite integral A to B. Okay, right to left is going to have opposite area as left to right if we do that integral. All right, if we take two integrals, the integral from A to C plus the integral from C to A, basically C is in the middle of A and B. If we add them together, it's really the integral from A to B. So if we go A to C and add it to C to B, that's the same thing as A to B. Those three properties right there will be more helpful for what we do in the second half of class. These next two will be the most helpful for what we do today. Okay. The first one is if we have addition or subtraction inside of our integral, we can split it up into two integrals. I think maybe we did talk about that when we talked about basic antiderivatives. So let's go ahead and talk about it again. It is okay to do this. And then our last one, if we have a constant inside of our integral, we can move it to the outside of our integral. Okay, that's also something that we talked about with our antiderivatives, our indefinite integrals. The same rule applies for definite integrals. Okay, so we're going to perform some calculations. Now we're only going to do one. Okay, we're going to find 4 different limits. And once we do these, we can remember what they're going to be. First one, write it down. Okay, this is the same as the limit. As n approaches infinity, we have this 1 over n, and then what's the summation from k to n of 1? It's going to be. Okay, over half of you got an A on your quiz. Help me out. N. For summing up the same number over and over, we multiply that number by how many times we're adding it together. So sum from 1 to n of 1 is n. Let's remember our limit rules. Basically, we have the limit as n approaches infinity, 1 over n times n is 1. So our limit as n approaches infinity is 1. Next one. So we have the limit as n approaches infinity of 1 over x squared times the sum from 1 to n of k. So we have the limit as n approaches infinity of 1 over n squared. If we're adding up 1 to n of k, what is that the same as?
Okay. Specific form. Is it n times n plus 1 over 2?
Uh-huh. Here's where those formulas are coming back at us, okay? Now we need to take this limit. If it helps, I'll go ahead and rewrite it as n squared plus n over 2n squared. We have a limit towards infinity, and our degrees are the same in the numerator and the denominator. What do we look at? The coefficient. So what's our limit, Isaac? Our limit is 1/2. When the degrees are the same top and bottom and we're going towards infinity, we can look at those leading coefficients. Okay. 2 more. We have a k squared and then a k cubed. So here we go with k squared. Okay, here we have the limit as n approaches infinity of 1 over n cubed, the sum from 1 to n of k squared. Grant, what's that shortcut?
It's n times n plus 1 times 2n plus 1 divided by 6.
Very nice. Now, I'm not going to go through multiplying that out, but if we multiply all that out, what would be the degree of the numerator? Cubed. What's the degree of the denominator? Cubed, okay. So we need to look at the leading coefficients. What would the leading coefficient in the numerator be?
Those 2.
2.
6.
Numerator would be 2. Denominator would be 6. So 1/3 would be our limit. Are you seeing the pattern? I hope you are.
Yes. Yes, but not going to keep.
Okay, Cole, so what's our next limit going to be?
1/4.
We'll find out. No, we will find out. Not a baby. Okay, so we have the limit as n approaches infinity of 1 over n to the 4th of the sum from 1 to n of k cubed. So we have the limit as n approaches infinity, 1 over n to the 4th times, Cole, what's our shortcut?
k cubed, n times n plus 1 over 2 squared.
Okay, I'm not gonna multiply that all out, it's not worth our time. However, we know that if we do n times n plus 1 and then square it, we're going to have a 4th degree polynomial in the numerator. In the denominator, conveniently, we have a 4th degree polynomial. So as we go towards infinity, we can look at the leading coefficients. Leading coefficient in the numerator will be 1, and the coefficient in the denominator will be 4 because of that 2 squared. At this point, if you don't want to take the limit every time, you can remember 1, 1/2, 1/3, and 1/4. Okay, I'm not going to know the difference. Okay. So, let's put everything together. Please do not write anything down from the next slide. We're just going to talk through it. Okay? So, what we're going to do, we're going to have a closed interval over a function from A to B. It's just in general. All right? And then what we're going to do is we're going to partition, means to like break up. Okay, we're going to break up A to B into infinitely many pieces. All right? The width of our intervals are going to be delta x, right? We've been used to that notation. Okay. C is going to be a point in the subinterval. So this is how we're going to add up our rectangles. Okay? And this is kind of what you wrote down earlier. Okay? As we're going to do this with rectangular partitions, not trapezoidal. Trapezoidal would be way too complicated with the algebra. So we're going to keep it simple. We're going to keep it as rectangles. And when we take the limit towards infinity, that means the number of partitions will approach infinity, and then our width will be infinitely small. Okay? So by doing this, by doing that limit and creating the infinitely many rectangles, we get the exact area. All right? So we come back to this. This you already wrote down. Now, what we are going to do, because technically we know 3 ways to do these rectangle approximations. Left, right, and mid. All right? We are going to use right-hand rectangles. It will actually make the algebra easier for us. Okay, you want the most efficient way, you want the easiest way algebraic-wise, right? The less algebra, the better. Okay. So if that is the case, then these right here, x sub k. Okay, if you think about it, when we do right-hand endpoints, if we're going from A to B, do we want f of a as one of our heights? No. We take a and we have to add the width, and that's where we start. Okay? So, delta, or our, what we plug in first is going to be a plus delta x, and then we'll multiply that by k to get, each of those individual rectangles. First, we take a and we add delta x, and then we add delta x again, and then we add delta x again, and then we add delta x again k times. Okay, so this is giving us that right-hand endpoint. So this is what we're going to do. You're going to be given something that looks like this, a definite integral. We're going to take it and we're going to set this up using our right-hand endpoint, and then we're going to evaluate the limit, and that's going to give us the exact area. Okay. We're going to do 2 examples, and then you are going to do 2 problems in your homework. What are you doing, question? Okay, so I have a picture for you. You don't have to draw the picture down if you don't want to. Okay? But if this is 2, 4, and 6, we have area over what interval? 0 to 5. So this picture right here means we're taking the integral from 0 to 5 of x squared dx. So if we are using right-hand rectangles, we always need delta x. And we find delta x by taking b minus a over n. The only difference here is that n is going to stay as n. All right? So b minus a, 5 minus 0. So our delta x is 5 over n. When you're doing a Riemann sum, everything's going to be in terms of n and k. Okay? From the previous slide, if we're doing right-hand endpoints, then x sub k is a plus k times delta x. Okay. What's our a value? Where does our interval start? 0. So a is 0 plus k times our delta x is 5 over n. So 5 over n k is that x value that we're going to plug into our function. Okay, so we said that a definite integral is this summation right here, right? Okay, well, what is f of x? What is our function?
X squared.
X squared. So what we need to do is we need to take x sub k and we need to plug it in to f. So if that's the case, we take x sub k, 5 over nk, and we plug it into x squared. So that's f of x sub k. Then we have delta x, which we found to be 5 over n. Okay, so if we multiply this out, we have 5 squared over n squared k squared, and that is being multiplied to 5 over n. So what we have is 125 over n cubed times k squared. Do you agree? Grant, do you agree? So we have 5 squared, which is 25,
Yeah.
times 5, you get 125.
Definitely.
N squared times n would be n cubed. And then this k squared here.
What is it n on the denominator though?
Yeah, but it's being squared. And it's multiplied to this n in a denominator. So n cubed. Cole, what was your question?
Nothing, I got it.
Okay. All right. Now, anything that is not a k can be moved to outside of the limit, okay? So we can rewrite this, no, excuse me, it can be moved outside of the summation. Okay, so we can write this as the limit as n approaches infinity. We can take that 125 over n cubed and move it out of the summation because we're only adding up k's. Okay, this is why notation is so important. Okay. Our shortcut for the summation of k squared, we know it is n times n plus 1 times 2n plus 1 all over 6. We've already talked about this limit right here, right? Larry, what did we decide that was?
One-third.
1/3? So basically what we have is 125 times 1/3, which is 125 thirds. That is our exact area.
Any way we can prove that it's not exactly right?
We just did.
Like, how do we prove stuff?
That this is the proof. Okay, now, I know that there are a lot of steps, which means you need to be organized with your work. Take one step at a time. Don't try to do too many steps at once. Okay, we're going to do another example, and then you're going to do a couple together at your table.
We do a number of that.
I don't think they'll fit. Did you guys have a question over here?
He wasn't sure if there is it if it was truly exact, because how could you if this is the proof, then how do you actually?
How do you actually know?
Almost like
Well, like if you take an infinite number of rectangles, there's still rectangles under a curve.
But they're infinitely small, so they're infinitely big. So they're like,
So it's
I mean, they're like paper
it's like a
thin.
line, basically.
Yes. So we're adding up a bunch of lines as if you need to visualize that. Does that help, Joe? Okay. Next one.
Still coming down out there?
So the interval is from -2 to 2.
Still coming down.
Yeah.
Okay, so you said the interval is -2 to 2?
Yes, I did.
Very good. We are finding the integral of -2 to 2 of 4 minus x squared dx.
Then 4 minus x. Oh, you're right.
Thanks, though. So the first thing we need to find is delta x, same as any other time, b minus a over n. So in this case, we have 4 over n. It should always be positive. Then our x sub k.
Forget how to do.
You're always going to take where you start, a, and then add delta xk. A plus delta xk.
Where does the K come from? I can understand like K plus delta X.
Uh-huh.
I don't know what like the K is factored in.
K is the number of rectangles that we have. And then when we take our limit, no, hold on. N is the number of rectangles. Yes, sorry, I misspoke. So K is taking into account. Let me get my words out here. K is any rectangle that we pick out. So it could be the first rectangle or the second rectangle, or the third rectangle, or the fourth rectangle, or the fifth rectangle. Does that make sense? All the way until N. Does that make sense?
Individual.
Yes.
Like it's super small, right? So it's big.
Yes. Because when we take the limit towards infinity, it squishes them to be infinitely small.
How do you plug that back in?
Okay. Remember, our integral is the limit as n approaches infinity of the sum of k equals 1 to n f of x sub k of x. So, how do we plug this in? What we do, Cole Smith, f of x sub k. That means we're plugging this in right here to our function. So our function is 4 minus x squared, and then delta x is 4 over n. So we have 4 minus x squared times delta x. Yes, we're going to have to do some algebra. The first thing we need to do, yes, is FOIL this out. Okay, when we FOIL it out, we should get 4 minus, when we take our outside and inside product, we get negative 8 over nk twice, which is negative 16 over nk. And then when we take our last product, we get 16 over n squared k squared. Do you agree with my foiling, I guess, is like you like to call it? Jake, do you have a question? No, just processing. Okay. So now we need to make this look a little bit nicer. Hey, what happens here? Maybe. Maybe does. And then keep in mind we're subtracting, so we have 16 over nk minus 16 over n squared k squared times 4 over n. We're getting closer. So now we have 64 over n squared k minus 64 over n cubed k squared. And if you think back to those limits that we did, yes.
Where are you getting the subtraction there? It's negative 16 and...
Because when
Oh,
we
you're...
Yep, right there. Okay? If you... What? You can question me all you want. Okay? Sometimes I make mistakes. Like cheering for K-State. I'm just kidding. I'm just kidding. You notice how we have the n squared and the k together, and the n cubed and the k squared together. Okay, things are going to work out nicely for those limits that we did earlier. Okay, so what I think we should do is we should break this up into two limits and two summations, like we said was okay to do. Okay, so first I'm going to write the limit as n goes to infinity. I'm going to take the 64 over n squared and bring it out. And then we have the sum from k to n of k. And then I'll subtract the limit as n approaches infinity. I'm going to bring out the 64 over n cubed, and so then we can focus on the summation from k to n of k squared. I will tell you that the one problem that you will have on your test and the one problem you'll have on your quiz will be the longest problem you'll have in this chapter. Okay? I know it's a lot of work. I know. But we got to do it. Okay. The shortcut for the summation of k is n times n plus 1 over 2. And then the shortcut for the summation of k squared is n times n plus 1 times 2n plus 1 over 6. Okay, if we group all of these together, what is that limit? Okay, what I circled in red is 1/2, which makes 64 times 1/2, 32, right? What I circle in red here, what was that limit? We already evaluated it today. Huh?
64.
Okay, so what I have circled in red is 1/3, so we have 64 times 1/3. So 32 minus 64 thirds.
160 thirds.
Yep.
Is it always going to work out where the powers are the same?
Yep.
We'll do fraction.
Yep. Nice, right? It's always going to work out where you have one of those 4 special limits, which is why we went through those 4 limits. So when you get to here, you know, I know that's 1/3. I know that's 1/2. We have a simple calculation. Okay? Once you get to here, you can take a breath and just plug it. Okay? Yeah. I can't.
How was it really? 162 minus 1. How was it 9? Oh wait, I added.
You added?
So that should be.
What should it be?
32. That should be 1, 2. Or no, 32.
32 thirds? Okay, thank you. Okay, 32 thirds. Did you fix it? We had a miscalculation. 32 thirds should be your answer. Okay. We still have an hour in here. What we're going to do for the next 20 minutes.
Talk about the K-State.
Nope. This is your assignment. I would like you to work on numbers 6 and 7. No.
What? Or we can have some time.
I'm giving you time to work on 6 and 7. And then the second half of this lesson, you're going to be like, Thank you, Mrs. Holman. This is so much better.
Speaking of
Okay.
second pass, I can that.
You were shaking in your boots, weren't you?
Did you watch or something?
Um.
Okay.
Okay. So let me tell you this. On your quiz, you will have one Riemann sum problem. On your test, you will have one Riemann sum problem. Okay? However, is it an efficient way of finding area under the curve?
No.
No. So now we are going to use some geometry. Okay? To find exact area under the curve. For example, the integral from 1 to 4 of 2 dx.
6.
Write it down, draw the picture.
Wait, what's the second combination?
4.3, continue.
Oh.
Our function is 2. The line y equals 2. Our interval is from 1 to 4. Cole, what's the area?
6.
How did you get that?
4 times 2. Oh, wait. No, wait.
How did you get that?
3 by 2.
3. The answer is 6 because we have a 3 by 2 rectangle. There's the area under the curve. That is the integral from 1 to 4 of 2 dx. Way better. If it's a basic geometric shape, we can find the exact area with geometry. That's
fear.
a sphere is three-dimensional. We're working in 2 dimensions. Write down the integral. Draw the picture. So we have the function x plus 2 in the line. Slope 1, y-intercept 2. And we want the integral from negative 1 to 2. You can do one of 2 things. What's one thing you can do, Austin?
Well, technically you know what the angle measurement is based off the slope, which we could do. So, that would be.
You're thinking way too complicated.
Yeah,
Where all we have to do is find the area. So you're talking about a triangle, right? Okay. You can split this up to a triangle and a rectangle. That's what you're thinking of, right? What else could you do? You can find a trapezoid. Does it matter what you do? No, because you're going to find the area the same. Okay, if we do a trapezoid, we have 1/2 times the height, which is what? 3 times the sum of our bases. 1 and 4, right? So 15 halves is our area.
So 1 and the 4 would be on the sides.
Yep. So this is the height. And if you're confused, like, you can always use the curve to get those heights. Okay. Or if you don't really like trapezoids, split it into a triangle and a rectangle. Nothing wrong with that. Okay. All right. Cole, I do not have a sphere,
Circle.
but I do have a piece of a circle. Try it. The integral from 0 to 1 of square root of 1 minus x squared dx. Square root of 1 minus x squared is actually a semicircle. Okay? That would be the entire curve, but we're only asking for the integral from 0 to 1. So we want the area under the curve from 0 to 1. Joe, how do we do it?
Well, I was just gonna do pi r squared and then divide by 4. since it's-
Pi r squared and divided by 4. What is our radius?
1.
Exact area without a Riemann sum. That would not be a Riemann sum you would ever want to do because of that radical. Okay.
Is that a challenge?
No, it's like you don't want to do it. You can't. I don't think you have the knowledge to do it right now. Now, here, no, I'm not saying that the whole I can't. I'm saying that. Okay, so here is one instance where you can think geometry. I know some of you have some bad memories of geometry, but here's a case where geometry is saving the day. Okay? Now, Austin and Joe were asking me earlier, what happens if the curve goes below the x-axis? What do you say, Isaac? Negative area. That is a thing. Okay? If we have area under the x-axis, then it's going to be negative area. This is the only time in your math career where you can have negative area. Anything that is below the x, if you have the curve below the x-axis, we think of that as negative rectangle height, which sounds very awkward, but that's what it is. Anytime we're finding an integral, we're finding area from the curve back to the x-axis, okay? So when we're above the x-axis, we're finding it under the curve, right? When we go below the x-axis, it looks like it's above the curve. We're always going from curve to x-axis. So if we're below the x-axis, we have negative area. Okay. So go ahead and draw this picture for me, including the A, B, C, and D. Draw this picture, labeling A, B, C, and D, and labeling those areas. Jake, what's the integral from A to B of f of x? Is it just a 5? It's just a 5. Logan, the integral from B to C of f of x dx
-4.
would be -4. Good. The integral from C to D of f of x dx would be what, Jennifer? B3?
What's A to B? 2 to the 5 plus 3 minus 4.
Let's answer Cole's question. The integral from A to D.
On 4.
Think so? Anyone else agree with him?
Not too sure.
Yeah. We add up all of our areas. One of them's negative. We end up getting 4. Okay. On the next page, there is a graph. I'd like you to take some time to draw it to the best of your abilities. Okay, I'd like you to take 30 seconds and discuss at your table how, don't do it, but discuss how we would find the integral from -7 to 5 of f of x dx.
Two triangles, you have like positive area, and then you have an So I would try to.
Okay, pod 4, what are we gonna have to do? Okay. Okay, so find the area here. Okay, that's it? That's all we have to find? All the way to 5?
In the circle. And then in the triangle.
Then we have it. Okay, so we have 4 calculations to make. We have negative area to account for here, positive area in a semicircle, positive area in this triangle, and then we have this little triangle here.
Told you. Boy.
That we have to account for negative area. Okay? So, how do we find area of a triangle? 1/2 base times height. So I'm going to put negative 1/2. We have a base of 5 and a height of 1. Then we have a semicircle. So we have 1/2 of pi r squared. Well, I guess I should do this in red. What's the radius of our semicircle?
2.
So we have 1/2 pi r squared. And then we have another triangle. So we have 1/2. The base is 2.5. So I'm going to call that 5/2. And the height is 3. And then we have to subtract out this tiny triangle, 1/2 base times height. The base is 1/2, and the height is 1. So we end up getting negative 5/2 plus 2 pi plus 15/4 minus 1/4. What's our area?
2 pi plus 4. 2 pi plus 4. What is it again?
That's that lesson. Now, one more thing, and then almost the rest of the time is yours. We talked about all of these properties. What I'd like you to do is go ahead and write down those 2 integrals right here, and then we're going to find some integrals based on what we know here. Okay, so write those 2 down so we can find some other things. In order to find the integral from 0 to 7, Sammy, what are we going to have to do?
Just add them.
Sammy asked, do we add them? Yes, we do. Okay, this is the same as the integral from 0 to 5 plus the integral from 5 to 7. You don't have to write that. What you need is 10 plus 3 is 13. That's our integral. Okay? Yes, you are right. How about the integral from 5 to 0? Trevor, what would that be? Almost. We're going from 5 to 0. Negative 10. Since we're going backwards, we're going to take 0 to 5 and we're going to negate it. Integral from 5 to 5 of f of x dx. Not even going to give me a chance to ask anybody, are you?
Because you can't start and end at the same place. You don't have anything there.
Yes, that would be 0. I taught you all of it. Integral from 0 to 5 of 3 f of x. What do you think?
30.
Okay, remember we can move a constant to the outside. So we have 3 times 10, which is 30. Woo! Aren't you glad we don't have a block schedule?
We have like 2 minutes.
2.
So we get out of here.
We get out of here at 10:05.
It's Wednesday. How does that work with block schedule?
We have an hour and 45 minutes for each class.
Wow.
So we started at 8:20. We have until 10:05. Now, here is what you are adding on to the assignment I've already given you. We have 15 minutes left in class. If you haven't finished 6 and 7, that's your first priority. Okay? And then from there, you can decide what you need to do from the first assignment and second assignment. Now, unfortunately, our block scheduling has you on the second day. So we're moving on tomorrow. Okay? This may be one of those times where you focus on the bolded and underlined problems. Okay? So, 15 minutes, you need to be working. We are not discussing snow. We are working on math, on calculus. I'll be even more specific than that.